If you are staring down a Unix semester exam, the syllabus looks like an impossible list of disconnected commands. This mind map translates that massive syllabus into 5 manageable, interconnected units: Unix architecture, system administration, development tools, shell programming, and C portability. We are stripping away the filler. This breakdown focuses exclusively on the high-yield topics and essential commands guaranteed to show up on the test. To pass, you don't need to memorize a textbook. Ken Thompson and Dennis Ritchie developed Unix at Bell Labs in 1969 as a developer-first environment. You need to see these 5 units as a single cohesive operating system pipeline. This diagram illustrates Unix architecture. Hardware sits at the center, wrapped by the kernel, surrounded by the shell, and capped by user utilities. The kernel manages memory and hardware. Users never touch the kernel directly. They send requests through the shell. Inside this system, the governing philosophy is simple. Everything is a file. That includes standard text documents, directories, and even physical hardware devices. This tree diagram maps the standard hierarchical directory. For the exam, know the distinct roles of these subdirectories. /bin holds essential user binaries. /etc stores configuration files. And /dev contains the device files representing your hardware. Because everything is a file, security is handled through a strict mathematical permission system. Read is assigned a value of 4, write is 2, and execute is 1. When you see a command like chmod 755, it's basic addition. The owner gets 4 plus 2 plus 1, a 7, granting full read, write, and execute access. The group and others get a 5, which is 4 plus 1, giving them only read and execute permissions. Unit 1 establishes the physical laws of the OS. The kernel is the engine, and strict file permissions act as its security guards. Unit 2 moves into system administration, the process of configuring that core environment. A primary task is mounting, which is how administrators attach a new file system or device directly onto the directory tree so it can be accessed. This table is the /etc/fsabl file. The OS reads this file at startup to automate the mounting process, mapping specific devices to their designated mount points and specifying the file system type. Startup is a strict sequence. BIOS initializes hardware, passing control to the bootloader, which loads the kernel, triggering the init process. Init dictates the state via run levels. 0 halts, 1 is single user, 3 is multi-user, 5 is GUI, and 6 reboots. Once the system is running, user access must be managed securely. Basic account information like usernames and home directories are stored in /etc/password, but the actual encrypted passwords are kept isolated in the /etc/shadow file. Administrators modify these files using standard commands: useradd to create accounts, usermod to alter them, and userdel to remove them entirely. To protect the data generated by those users, administrators rely on backup utilities like tar for archiving files, dump for securing entire file systems, and rsync for syncing directories. System administration is simply the systematic configuration of the boot sequence, hardware mounts, and user access protocols. With the OS configured, Unit 3 introduces the standardized software development pipeline used to write and deploy C programs. This pipeline runs left to right. First, lint performs static analysis to catch syntax errors. Then make automates the compilation. dbx provides source-level debugging. And finally, strip removes the debug symbols to reduce the executable's final file size. The make utility relies on a makefile, which follows strict formatting rules. You define a target and its dependencies, and the crucial detail for the exam, the execution command below it must always be preceded by a strict tap space, not spaces. For tracking changes across multiple code edits, you use SCCS, the Source Code Control System. To save disk space, it only stores the deltas, or the exact differences between versions, rather than saving full copies of the files. If you are building a compiler, the pipeline requires 2 specific language development tools, Lex and Yak. Lex acts as the lexical analyzer. It reads raw input text and breaks it down into distinct categorized tokens. Yak, the parser generator, takes those tokens and checks them against predefined grammar rules to ensure the syntax is mathematically valid. Unit 3 provides a robust toolkit to build and verify raw C programs, preparing them to be automated by the shell. The shell is a command line interpreter that acts as the functional interface between user-facing commands and the hardware managing kernel. Shell scripts rely on special variables shown here. $0 stores the script name, and $# counts total arguments. The most tested is $?, which holds the exit status of the last command. A return value of 0 confirms execution was successful without errors. Scripts use these variables to drive conditional logic, relying on standard if, elif, else blocks, and case statements to route execution paths. Inside those conditions, you evaluate data using test operators. -f verifies a regular file, -d confirms a directory, and -z checks if a string is completely empty. The shell also natively handles multitasking. By simply appending an ampersand to the end of a command, you detach it from the active terminal and push the process to the background. You retrieve or manage those background tasks using explicit job control commands, fg to bring a job to the foreground, and bg to resume a suspended job in the background. Shell scripting provides a method for integrating individual commands, conditional logic, and background tasks into automated sequences that run without further manual input once triggered. The final unit strips away the high-level shell, dropping down to the bare metal to examine system calls and inter-process communication in C. Every high-level library function, like printf, is actually a user-friendly wrapper. Underneath, they trigger low-level raw system calls, like write, to request action directly from the kernel. The fork system call creates processes. It returns 0 to the child's PID to the parent, or -1 on failure. The child uses exec to load a program, while the parent calls wait until the child finishes, preventing zombie processes. When those separate processes need to share data, they use inter-process communication, or IPC. Pipes are the simplest method, establishing a unidirectional data flow between related processes. Contrast pipes with shared memory, which maps a single memory region across multiple processes to provide the fastest IPC method by avoiding data copying overhead. To prevent data collisions in that shared space, processes use semaphores, which strictly control access without sharing data themselves. Unit 5 is the bedrock. Every shell command, user utility, and administration tool ultimately relies on these C system calls to communicate with the kernel. Stepping back, the scope of the exam comes fully into view. This map shows the complete operating system lifecycle. You establish the layered architecture and permissions of the kernel in Unit 1, configure it to boot and manage users in Unit 2, and build development tools on top of it in Unit 3. Shell scripts automate those exact tools in Unit 4, and those scripts natively execute via low-level system calls back in Unit 5, feeding directly into the kernel where we started. Memorizing isolated commands won't be enough. Passing the semester exam requires understanding this pipeline, a single integrated machine from the hardware up to the shell.